Yeah, so why don't I get started? And first of all, I want to thank those who are attending remotely. And just get started. This will be recorded, so you can see that later, as well as the slide deck should be available as well. It is a historical issue of this series because it's the last one that we're planning on doing. So again, thanks for attending. The biomedical and healthcare data discovery index ecosystem started in March of 2015, so we're 2.5 years into it right now. And what I intend to do today is to show some of our accomplishments and talk a little bit about next steps and hopefully have a good discussion with the group. The steering committee for this project is composed of an executive committee that meets frequently, as well as members of the steering committee that meet every month. So they're listed here. And the reason for me to present this is to say, even though I'm the spokesperson today, there are a lot of people involved in this project, some of which are shown here, and some of whom have been working in different parts. So it's a large consortium, and I'm here to present a few things of what we're doing. The Data Discovery Index Consortium had 3 goals: of help users find shared data, build a prototype data discovery index, a search engine for data, and then interoperate in the NIH Commons, all under the FAIR principles of findability, accessibility, which are our main targets for bioCADDie's products right now, but keeping an eye into interoperability and reusability of those data. And our motto is to do for data what PubMed did for papers. So the same way you search across journals, articles, our intent is to search across repositories to find data sets. There are phases to our project, and the phase 1 was to find and index repositories or journals in order to have a populated search index that people could start using. And we relied on bioCADDie's indexing team reaching out to repositories to actively map their metadata to DATs. On a phase 2, we facilitated that mapping into DATs, but that was done by the repositories with some assistance. And we integrated the data sets, when I'll put in quotes the equivalent to articles, a search across all repositories using DataMed. And in phase 3, it's to, again, become even more scalable so that the mapping occurs almost without any assistance from the bioCADDie team, and is done by the repositories themselves. And then also one aspect that we find important in order to rank the data sets of interest, which is to look inside the data sets. Because there are instances in which the label or the metadata of the data sets will not indicate, will not give us enough hints that that particular data set has data that we're looking for. So going one step deeper into indexing is what we consider an important follow-up as the other items become more self-doable by repositories, by authors, in that we can concentrate on the indexing. So here a particular use case, finding all data about astrocytomas grade 2 with IDH mutations. And the reason I was looking into that is to answer the questions: what are the recurrence and mortality rates for an 18-year-old who just had a biopsy or a surgery and had that particular configuration? And this is very hard to find. We may have electronic health records potentially available under access controls. We might have images we might have other sources of information. So how do we go about and create a data search engine that would go across all internet assets and find the ones more relevant to my question here? If you go on Google, as you will see, there's no such thing as a label for data. In the future, it might be, and bioCADDIE has a role into that by making our indexing available through schema.org and being findable by Google as well. But right now, if you Google exactly this set of terms here, what you will find is a blog. You will find some literature on PubMed and comments and other things. You will not find the data sets currently, which is why we created the prototype search engine. We indexed 74 repositories containing 2,300,000 or so data sets, in that you can type that very same set of terms and then get a link to data sets. So if you do that, again, remember the terms that I was typing before, you will have return of data sets from several repositories getting back to you. And then you will have options to select the repositories, the data types, to filter those facets, and know how many were published in each year, have synonyms and other things. But the whole idea here being that it's a search engine for data sets. The way it works, there is this, the repositories or data sets are out there, and we have sponsorship from the NIH in this case. We have engaged data producers and publishers in order to know there is a process for metadata ingestion. Each data set has metadata about it, and it's ingested and mapped so that we're all talking about the same metadata. And there is then a search engine that goes and searches through those metadata with query extensions and then presenting the results in a ranked order. And then what the users see on the outside is exactly the data search engine without seeing the intrinsics that are the metadata that are used and how it is transformed from their original sources into bioCADDIE through the DATS specification. And remember the data sets I got in that search that I just did in DataMed. Number one was genome-wide profile of astrocytic gliomas, and the other one was expression profile of lower-grade diffuse astrocytic gliomas. So one data set had 131 observations, the other one had 101. How to rank the data sets without looking into observations? And what guarantees that there can't be another data set, let's say in a surgical data set, that would have many more of such cases, but whose metadata was not indicating a preference towards this particular histology type. So it might be that a larger data set of gliomas, including astrocytic or not, would have more than 131 cases, and that might rank higher in relevance for the user. So what's happening right now, we do feel that it's very important to consider some indexing that does refer to indexing the observations themselves or producing some statistics about commonly searched items such as diagnosis, grades, or other entities. So biomedical researchers reuse data as reference, as controls or artificial controls and benchmarks. They reuse software to process and analyze their data, and they produce original new original data from those items, or derived data from those items. And then they publish results that are themselves data. So there's a hierarchy of data items, from what we would call the raw data to pre-processed data to analyzed data and to aggregated data. So if you think about the whole cycle, it could go from the data that you get from an original instrument all the way to the analysis of that data, all the way to the systematic review of several studies of several of those results. And these are all data sets which we need to find. So researchers look for data that happen to be aggregated in data sets. And this illustration here is just to say that repositories have several data sets. Each data set has metadata of author, types, standards used, landing pages, etc. And currently, that's how we are indexing the data sets in bioCADDIE, whereas there are other levels of indexing. For example, there are variables or data elements or dimensions in each data set, and you might want to be searching for a particular diagnosis. Therefore, only data sets that have a diagnosis dimension would be of interest to you. And as I mentioned, grade, histopathology type, or imaging, and so on. And more deep, even deeper level would be to index at the level of the values in those data elements. For example, a particular age groups that you're looking for, grades, or a particular histology type. So as you see, we are still on this phase here of metadata indexing for data sets, but there are other depths that we think are important when ranking the returns of results when you do a query on a data search engine. And here in this illustration is just to recap what I had mentioned before, that you can have the so-called raw data, and it has some metadata associated with it. Then you have software that are themselves digital objects that have metadata associated with them. And when you utilize those software, those analytic systems on top of the raw data, you create yet another data set which is derived. This could be software that cleans up, removes outliers, and then you have pre-processed data. It could be software that uses the pre-processed data to generate a model, and then the coefficients or the parameters, parameter values are the derived data, and so on. So there are a lot of things that we name data, and that we might even just call them digital objects, because they all need to be indexed in order for us to be able to reproduce results and to leverage existing results and take them to the next level. So in this figure here, just commenting that big data analytics depend on merging data from several different sources. For example, reference databases, public databases, and so on. Having the proper software to process and analyze those data, and then the proper computational environment to do so, given that some data are protected, need to be in certain environments, some need parallel processing, some need even GPUs and other things. So it's important to couple data, software, and the computational environment all together. And like I mentioned, there is transformed data, there is reference data, and there are aggregates of those as well. When you deal with protected health information, which is our case with electronic health records and clinical trial data, when identified or in the form of limited data sets, you have to make sure the computational environment is also taken into account, and all the access controls that need to be put in place in terms of technical and policy decisions. So the big data ecosystem is actually that you do all this, and then you produce new, what we would call new original data that can go through this process all over again of pre-processing, generating results, and those data being themselves analyzed. So like I mentioned before, data science organize, integrate, and analyze data from various modalities, be signals, imaging, clinical, omics, etc. And they produce systems, tools, containers that populate this NIH or this even larger biomedical research and health sciences research big data ecosystem. So a lot in here to think about as we start with the tip of the iceberg of indexing data sets, but there's a whole lot more that needs to come together for this ecosystem to operate. In terms of the data ecosystem in particular, we're indexing, meaning we're labeling, we're cataloging, we're tagging. And what happens just in this illustration, you have data sets such as this one that has as data elements date of birth, diagnosis date, the particular diagnosis, the grade, and a particular marker. So it's represented in a certain way here. And if you want to merge that data set in order to have a larger sample size, let me pretend those are two registries, for example. And the second registry is organized differently, in which it doesn't have date of birth, but it has age, and it has the diagnosis coded in a different way, and each column for the known markers for neurological cancers, for example, like IDH positive in one column. This data are completely mergeable, but there have to be transformations in order for them to add up. So you would use metadata to understand what each data sets are. You would use the data dictionaries, and then you would harmonize into a common data format, which could be, for example, the aging year at a particular date, the use of diagnosis from a terminology standard, such as SNOMED CT or ICD-10, and then the gene symbol and the results. So that's just an example of how you would harmonize data, and then you would be able to have data from both data sets aggregated and therefore result in a larger sample size, for example. That sample size could, let's pretend you're trying to do a predictive model of recurrence or a survival analysis model. Then you would have to transform that data once more into a format that is taken up by your statistical libraries, for example. And this is just an example of yet another transformation of the two entries in two different data sets, simplified, of course. And as I mentioned, as you create an analysis model, let's pretend this is a regression model, then you would have coefficients that go with it. And those coefficients are data themselves. So that would need to be indexed as well. So indexing takes a lot of things into account, like I mentioned, the data object in which we are concentrating this presentation on, but also software objects and containers objects, which make things even more modular and easier to reproduce. So bioCADDIE components, like I mentioned, we're focusing on data indexing at this point, and we found it important to have community engagement in order to understand and create the use cases that our products would address. And one of the important building blocks is to have metadata specifications that would go across repositories, because each one currently has its own strategy for having its own metadata specification. So what we wanted is to harmonize all those metadata so we could do operations so that we could find the data that we need across all the repositories. We also invested a significant amount of time on software development that we're calling the search engine DataMed. And as I mentioned, behind the front end that you will see in datamed.org, you will have all the indexing processes going on, and including by popular demand an API. So essentially, you can use all of DataMed on a different front end or integrate with your own applications. And also, as a means to engage the community, we have over time issued supplements and pilot projects that those are funded activities from bioCADDIE so that the community collaborators could contribute their own products and be integrated into ours. So the activity areas in bioCADDIE relate to that, this data specification, related to indexing, linking data to articles, ingestion of those data sets. And then the showcase, the front end, which is the search engine prototype, which used a lot of user feedback to implement new features. And lastly, a data market, because if we do all of this and there isn't a system that provides incentive to those who share data and that promotes the use of our products, then the impact is much lower. So we engaged several working groups, as I mentioned before, starting from use cases, to producing the use cases of a data search, then going for criteria for inclusion of repositories in the first version of our prototype, so it was sufficiently populated for people to understand the concept of searching for data. Also, unique identifiers are very important, persistent identifiers, and this was another working group dealing particularly with that question. Most working groups were self-contained and limited in time, but the data tag suite, the DATS, or the specification for metadata, this was one of the continuing ones because the specification needs to continually adapt to needs that we detect from the community in that are apparent as people use DataMed as a means to see, those metadata in practice. How can you search? You can search by this dimension, you can search by that feature, and so on. So we believe having DataMed, the prototype, and the specifications, it's important that they go together. Otherwise, you don't have a good means to test the usefulness of the specification. Parallel to that, there was a working group specifically targeting accessibility and metadata because we don't think just having public data sets indexed is the right thing to do. There are very many data sets that are under access controls that are of great value to the community, and they need to be indexed as well. And the users need to know, those may not be publicly accessible, but there are mechanisms to request access and obtain that access. So we wanted to codify the accessibility to those data sets as well, and that's what this working group did. We also had, like I mentioned, pilot projects done by others that we could incorporate into our search engine. Graphical user interface, results ranking were also important components of the search engine. And then on the data market, it's important to get data citations, links to publications, and so on. Finally, evaluation of whether those searchers are fulfilling some of the use cases. We of course, in a limited time of the 2.5 years we had from beginning the project until now, we cannot address all use cases, but many of them were encompassed and then were evaluated. Like I mentioned, there are several people working on this. This is some of the institutions they came from, and they participated either in working groups or pilot projects or supplemental projects to DataMed, with the common feature that everything created through bioCADDIE would have to be open source and available to all. So I'll do a quick run through the working groups, starting with the interactions with the BD2K Center and other programs, as we find it important to be part of a larger ecosystem, like I mentioned. So we original goal was to interact with 2 or 3 centers, and we are outnumbered that because a lot of centers did approach us and vice versa, given the common interests. So not only with BD2K, but also with other programs, we have been very integrated. There was a working group on identifiers, in which here I just want to acknowledge people from several different institutions. The recommendations are online on the biocaddie.org website, and you will see they are summarized here, but there is much more detail online. The working group 3, as I mentioned, worked in 2 directions in order to harmonize metadata across repositories. It used a top-down approach by using the use cases and formulating what metadata should be there, and then a bottom-up approach in which it analyzed the existing large collections and saw which metadata were there in order to converge with a common set that would be useful and relatively simple to map. And as I said, it's also mapped to schema.org so that those data can be discoverable by other search engines. Working group 4 was on use case and testing benchmarks, very important so that we stay in tune with what's the demand out there. Same applies. The report is online, and more details can be found there. Data citation metrics, also important for our data market segment. And again, same pattern, many groups, many institutions involved, and recommendations available on our website. There were qualitative and quantitative metrics to evaluate DataMed, the data search engine, what we call the bioCADDIE prototype, and to go about how to fix those. And very important, ranking data results, as we know, of any search engine, is as important as finding the data themselves. So that was an effort targeting ranking in particular. We also had, like I mentioned before, criteria for repository inclusion. So at this point, we are not claiming we are indexing everything that is out there. We thought it would be very important for the search engine to have some criteria in order to display those data sets or not. And we started with those 5 named here: prominence, sustainability, scope, quality, and access. And we have created some recommendations so that we would sequence the repositories that we were indexing by the bioCADDIE team. And of course, as we evolve and repositories approach us to be indexed, we apply the same criteria. Access metadata, as mentioned before, it's very important. So the user knows whether they can access the data set. So they found it, can they access now? What are the requisites in terms of authorization, authentication, and actual access? So there are metadata related to this particular items. Ranking search results, as we mentioned, is very important, and so we used the advice and the work of the community to help us go with ranking strategies and algorithms that would help with that. And user evaluation criteria, again, how to get feedback from the community and incorporate those feedback into our products was an important working group as well. In terms of repository contact and workflow, that's also very important. We counted on the developers and the maintainers of such repositories in order to get the mappings done correctly. And the more engaged ones, of course, resulted in higher quality mappings than those that we essentially only used information from the websites and from their portals. We have a working group on standard-driven curation best practices as well, so that is exactly on how approach the problem that in order to be scalable, this effort the mapping needs to be done by the submitters, the repositories who know better their data than anyone else and can do that mapping. So how to make sure they map into the minimalist specification that we have created in order to go across repositories. Finally, we had a working group on harvesting and NLP pilot projects. This was essentially what we transformed into a challenge activity, and this was the information retrieval challenge, or the data retrieval challenge, in which there were several teams from various different institutions, commercial or academic, and they were evaluated on several indices that, again, will be on our website, as well as many articles that are coming about each one of the solutions in very soon. And you will see, depending on the index, there were different rankings. We're in bold here, one of the objective indices that were used, but there were many others and many considerations, including how adaptable to our repository that particular solution was, how scalable it was, and so on. So like I said, metadata adoption, there are two fronts: annotating existing data, which was started with our own team, and we will continue so that we have a set of repositories that is representative of the most commonly used ones. There needs to be incentives for data producers and repositories to facilitate mapping. And one of those incentives is that if the mapping is done better, it's higher chances that the data from that particular repository would come at the top of the search results. There should also be incentives for data reuse and data citation, so that there is a virtuous cycle of citing and getting acknowledged, getting some material compensation for that, and then sharing even more. Annotating new data, like I said, there is, so PubMed has JATS, as the journal article tag suite, and we have DATS, and so it's a similar process. If a publisher is approved to be indexed in PubMed, they submit their entries in JATS, so they appear in PubMed. Same thing for DATS and appearing in DataMed. So additional resources need to be provided for data producers to prepare data for sharing. So while some large repositories self-sustain by several mechanisms, if you think about the smaller ones and even individual authors in the future, there should be some incentive for sharing, especially after grant funding period ends. So resources for data producers and our repositories to maintain data and their annotations are needed, and leveraging resources from various paid projects, consolidation of efforts, and incentivizing data producers or data keepers saves time and money, and that's one direction that we find very important to continue to pursue. Several data repositories contributed to this effort. Not all are represented here. These were some of the initial ones, and we hope to continue on two fronts. One, to make the mappings of those repositories better on, like I said, indexing data elements and variables and data values to the extent that we can. So improve on the indexing of these repositories as well as to add others. I think someone got very excited about this webinar, so thanks for having youngsters also attending. It's the next generation, and we need to have everyone pretty engaged into data sharing. So in terms of Data Shop and Showcase, that's how we envision it. The DataMed is the front end for our efforts, is what you will see when you do datamed.org. And the back end is the whole process of indexing, that consensus representation, and having the repositories wrap their data in a way that it can be discoverable by DataMed and others that use DataMed for their own purposes. Like I mentioned before, the repositories are data aggregators. There are many of them. There are individual data sets out there. In bioCADDIE, the discovery index is exactly to put them all into the same format so it can be searched across, and also to dock pilot projects and modules from others so we have a total product. And we have collaborated with several other centers in particular aspects of this integrated effort. An example of added functionality that was done by our colleagues from Links, led by Dr. Mayan at Mount Sinai, was to add information of which analyses were already done with these data sets, for example. So someone found a data set and maybe they don't need to reanalyze. Maybe they just need to find the results of someone that already analyzed for them. So that's an interesting feature. And because of our software being open source, it was easy, relatively easy for this external group to add their features into DataMed. We also had supplements for data citation implementation pilots that were granted to Force 11. Account Everything is a query across different repositories based on the same patients that we wanted to do it in a privacy-preserving manner. And we had collaborators from MD2K, Picture, and the Global Alliance for Genomics and Health in order to create that capability. We had pilot projects granted to different institutions. The first set is shown here. There was subsequently another set. And last year, we concluded the bioCADDIE data set retrieval challenge, like I mentioned before, and this is the geographic distribution of the parties that were interested and were submitting their entries into this challenge. So to summarize, the products delivered were DataMed prototype, the DATS metadata schema, the specification. 10 pilot projects were funded by bioCADDIE, and 5 supplement project collaborations, the ones that I'd shown in previous slides. In addition to that, there were 13 working group reports, and you saw them all listed before. And that's where we had so many people contributing to this. So the near future, as the project, or at least this phase of the project concludes, is to conclude that the pilot integration completes our core deliverables, find a home for DATS and DataMed. It's the continuation of this effort, in which we believe the two go well together, the specification and the means of showing the value of that specification through our DataMed search engine, and then continue discussions regarding DATS adoption and need for DataMed to check them. With that, I would like to conclude and acknowledge the effort of the consortium. This was, as I am the spokesperson here, there were more than 100 people in working groups and on pilots and everything working together to make this happen. There were 12 steering committee members that are dedicated in giving very important direction and insight into our developments. 8 pilot application reviewers for the challenge and pilot projects, staff and trainees and collaborators. So it was more than a village, I would say, to get to the point where we got. Our journey is towards a concrete, sustainable biomedical information commons. We find it very important. And what I put on the left-hand side is how we are beginning with this, with the DATS specification and DataMed, that my goal and the goal of all our members is that it become a long-term, sustained effort that is embraced by the community and is the success that impacted so many researchers and so many others, the same impact that PubMed had. We hope, and we are working towards having DataMed have a similar impact. There is an African proverb that says, if you want to go fast, you go alone. If you want to go far, you go together, which I adapted here for bioCADDIE. If you want to go fair, you go together. Again, this is an effort of so many people, and with that, I would like to thank our sponsors at NIH, everyone who worked together with us towards this effort, and the users who are giving us continuous feedback. In addition, of course, to the project program managers who work relentlessly to have the third version of DataMed available, as well as organize many workshops and other meetings. So with that, I would like to conclude and check. Hopefully there are some questions, comments, or remarks from those who are attending live.